You're listening to Weird and Dead, the paleontology podcast that tells evolution's most embarrassing and bizarre stories. I'm Amy Atwater.
And I'm Megan Wetherell, and we are two living scientists who are weirdly excited about dead things.
This week is all about brain fossils. Brains made of sand, of putty, and also those made by a computer.
We'll tell you all about an insane fossil brain bonanza in West Texas and stumble through medical terms for tissue that doesn't usually fossilize.
Flocculus! And of course, we talk about Tilly Edinger, the paleontologist who figured out what brain fossils were good for in the first place.
Like always, our podcast talks about some disgusting stuff.
Flocculus!
So please read through the content warnings before continuing.
Oh, God.
Okay. Today, we are going to start out on a story about the best animal in the world, Oreodonts. Oreodonts are awesome because I study them, but they're also awesome because they're extremely weird little hooved mammals. They're all extinct and it's very, very sad. But they're very cool and they're found in one of the coolest paleontological places in the world, which is West Texas.
Woo.
So in West Texas, there are a lot of different fossil beds. Amy and I have both done some research together at them. I don't think we've actually been to this particular one. And a lot of that was collected during the 70s and just I'm shocked that there hasn't been much more work there. But we're going to talk today a lot about brains. And we're going to start with a conversation about Oreodont brains. And specifically, there's a place in West Texas called Reeves Bone Bed. It's in the Chambers Tuff Formation. It's Eocene. And it's about 80 feet by 20 feet with a thickness of 3 feet deep. And it was described by Wilson et al. In 1971 as being like a paleontologist's dream, just because it's such dense bone. And it's not just bone. It has a lot of what we call endocasts. And an endocast is functionally just where something has taken the surface of the inside of the brain case. So it's not a brain, but it looks like a brain, and it takes the place of a brain. So it's sort of a sand brain. And in the Reeves bone bed, can you guess how many endocasts they have? They've collected more actually since then, but just by 1971, how many natural endocasts of Oreodonts alone do you think they found within 80 by 20 by 3 feet?
80 by 20 by 3. However, I have to consider that they're Oreodonts, so they die in herds and they're fucking everywhere.
These are not herd ones. These are little tiny ones. These are little babies. They were just delicious.
Okay. Well, okay. So they're small. So that means more of them could pack in per area. I'm going to go with 52.
157.
I was only off by 105.
Now, I will say that
holy crap.
In this study on basically their shapes in 2009, he looked at 157 natural endocasts that represented a minimum of 107 individuals. Because when we talk about endocasts, it's not always the whole fake sand brain. Sometimes it's half of the fake sand brain, and you can't guarantee that other sections didn't link up. That is still a minimum of 107 individuals.
They're not still in the cranium? They're not, some of them are just loose brains?
These are all loose brains.
What the
Yeah, these are...
Okay. Wasn't ready for that.
No. So that's the weird thing about natural endocasts, is natural endocasts are usually something where you have an infill into the brain case, so the skull gets filled with sand or dirt or something, and then the skull disappears somehow. Maybe it gets cracked and it falls off and the brain is harder. Maybe it, dissolves because it's not made of sand, it's made of calcium. So there's basically 107 loose casts of the inside of a skull.
Wow, I just have so many thoughts. My brain just went to the fact that UT Austin used to have the largest collection of human brains, just in jars, including of Charles Whitman and others. And so now I'm just and actually one of the primates I'm going to talk about is got a natural endocast and it's from West Texas. So what the fuck is with Texas and brains? I wouldn't put those two together.
I don't know.
Just kidding. Just kidding. I love everyone from Texas.
Yeah. Texas is great. Texas paleontology is definitely great. So someone needs to go back to Reeves' bone bed and actually write up like a sedimentological study. The only other information I could find about Reeves' bone bed was like this mention of an abstract that was published in 1989 at a conference at GSA, and I haven't been able to get a hold of the abstract. But the idea, from what I can glean from a secondhand source discussing an abstract, is that maybe this was a predator den that was just eating a ton of Oreodonts. There was also other small animals, Leptomeryx, which is a really, what is Leptomeryx? Is that a paleomoricid? It's a weird thing that isn't an Oreodont, but they kind of look like. Yeah. I think it's actually a leptomoricid. I think they're their own thing.
Oh my gosh! How dare you?
It's a weird little ungulate, a weird little artiodactyl.
Yeah, in the Eocene, they're all pretty weird.
Yes, and there's a ton of endocasts from them too.
Okay.
Yeah. So the Oreodont that they found there is probably Bathygenes, which is a really tiny little Oreodont. There's a bunch of them at UT Austin that have little tiny puncture marks in their skull that, again, someone needs to go study that. I'm not 100% convinced by the ambiguous mention of an abstract that thinks it's a carnivore den, because it's a little weird to have that many dead Oreodont. Maybe it's a collector, you know? But regardless.
And wouldn't they eat the brains?
Yes. Well, remember, these aren't brains. They are sand on the inside of a skull. But the weird part is the skull is gone.
But they didn't bust it.
Yeah.
Right. The skull is gone, but if the brains are largely intact, that tells me that at least the sand had to be within the skull for a period of time to get the shape right. Yeah. So that wouldn't be during the actual peri-mortem experience. That would be like taphonomy. Oh, right. Yes. Which is, here we go.
You know what?
Right.
Let's just talk about the taphonomy. I wasn't sure if we were going to fit this in, but
we have to.
It's kind of impossible not to, right?
Nope.
So there are not, as far as I can find, a lot of studies on the taphonomy of endocasts. We find a lot of isolated ones. So most of the papers about endocasts are like, we found a cool endocast. But with Oreodonts from this location, it's we found 107. And the one study that I could find, they were trying to figure out if they could actually identify all of these Oreodonts as Bathygenes reevesi. And they decided that no, probably it's not actually all one species. They weren't sure if it might be two different genera or not. But they only could conclude that because they were variable enough to be too much variation to be one species. They cannot link it 100% to this Oreodont. It's not 100% diagnostic for a chunk of you can't have a sand brain and identify exactly what it's coming from. But I haven't found anybody who's really looked into what are the consistent factors that are causing endocasts to form, because they're not very normal. They're not like a super common aspect of sedimentology. They're normal enough that most people who study paleontology know about them, but they're not normal enough that having 157 endocasts is like a normal collection. That's pretty weird. So the endocasts that I have found people doing studies on as far as taphonomy goes, I found one good study that did a study basically on a lynx endocast from Italy. And what they found was they took a look at the shape of the brain. They realized that when it was initially deposited, the skull was deposited probably in some sort of a river or a lake or something. And it was deposited with the foramen magnum, which is the hole where your head connects to your neck, probably in the upward position. And they realized this because it had stratigraphy infills inside of it. So if you looked at the endocast, because the skull was gone, yeah, you had really big stones that had come in, well, big compared to a lynx's brain, that had come in and been deposited initially. So like the top of the skull, but the bottom of when it was flipped over had bigger stones. And then there was another layer of like sand and another layer of silt. So they had like slower accumulation of different sizes of particles, indicating that the water was slowing down over time. It was also probably multiple events. So it's not like one big underwater landslide. Right. And then they looked at the outside.
I was going to say, this sounds like you're describing a Bauma sequence, that's exactly what you look for. But those are turbidites. Those are underwater landslides that you then are seeing the bigger grains at the base. But oh my God, that contained within a skull. That's the most metal thing. That's like the most geo-paleo.
You know what it is, though, is, I haven't found, they didn't say this, but I think that might be a geopedal, right? Like a way up structure indicating which direction is up. Yeah.
Yes.
Which is funny.
Yeah.
So bigger particles at the bottom, they at least tell you which direction the endocast was facing. And then on the outside of the endocast itself is a layer of basically like carbonate enriched like sediment. So essentially you had this skull sitting upside down. It got filled with a couple different events. So it was full of sand and rocks and things. And then over time, the skull itself probably leached some calcium into the outside of the little sand brain thing. And all of a sudden, once the skull had decomposed or been knocked off, there was enough calcium on this big lump of sand in the shape of a brain that it stuck around preferentially. So,
wow.
Yes.
Oh, paleontology is so cool.
Yes.
God.
And for some reason, in Reeves' bone bed, those brains are really preferentially preserved. I wonder if Bathygenes, unlike a lot of other oriodonts, has a really thin skull. So it's other oriodonts are like bowling balls with their head. So I wonder if Bathygenes, Bathygenes, I wonder if it was just a little bit too fragile and so they don't stick around. But we have a lot of endocasts of Bathygenes. Even though I think the story of the taphonomy is maybe the cooler aspect, it's definitely not what people love to study about endocasts. And in fact, natural endocasts aren't even the entirety of the story that we're going to talk about today. So a natural endocast is where the sand and whatever infills the skull and then somehow gets separated from the skull, at least partially. But you can, of course, simulate this. You can put mold compound into a skull and then break it open, and you can have like a replica of how the brain was imprinting against the skull. You can also do CT scanning, if you don't want to break the skull that you're dealing with. So studying endocasts has become it's become a lot more popular for sure, because we don't have to just wait until we can find sand brain casts. We can actually make them ourselves. So tell us about people who make them.
Yeah, and I love the CT scan aspect. I did a little of this actually, and what my question is immediately is with the Bathygenes, has anyone taken a CT scan of an empty, like a full skull that doesn't have an endocast, and then compared it to one of these loose brains to see if there's a general fit? Mm-hmm. Like, because you said there's no for sure ID, but that also costs money because CT scans are expensive.
That was what this paper from 2009 was they compared it it was actually a very good paper. I say actually because a lot of oriodont papers sadly are not, but it was a very good paper.
Megan is picky, rightfully
I'm
so.
I'm also very picky. But yeah, they took a CT scan of Bathygenes and they cross-compared it to a bunch of the brains. But they also, I think, discovered that, when you have a sandy endocast, sometimes it gets rattled around. So sometimes the features are kind of worn off.
Right.
And then just, it isn't super clear, at least at that point, there's enough variation that telling the difference between Bathygenes and Limnites, another small oriodont that was alive at the time, that we just don't have a good enough concept of their brain / maybe their brain isn't diagnostically different. Sometimes you can't ID a brain.
Science. Wow, it's very, very cool. And again, just like West Texas, thank you. Very, very cool place. So yeah, but where would we be today without some pivotal research from the founding paleontologists who created the entire field of paleoneurology, the study of fossil brains? And that was Tilly Edinger. Dr. Tilly Edinger, I should say. And her full name is Dr. Johanna Gabrielle Tilly Edinger, and she went by Tilly. So thanks, girl. Appreciate that. It makes my life a little bit easier today. And she was inspired, you're talking about natural endocasts, right? So those can form in anything that's hollow. We can find endocasts in other things. And it usually means brains, but sometimes it can mean like inner ear structures that we might talk about later. It can also be like nasal features, like your nasal turbinates, the little swirls in your nose. So it really just is like this perfect kind of, sedimentological replica of this hollow void. And that is how Tilly first got exposed to the fossil brains. And I will say for the record, she was born in the late 1800s. And she is the daughter of a very famous neurologist. So I will say for the record that she is a total Nepo baby.
You had to be at that point to be a woman in science, though. So...
Exactly. Oh my God. That's exactly what I was going to say is like, but so the fact that this woman pursued a PhD in 1920, it goes to say like, holy shit, maybe she did have an upper hand because of her lifestyle and her father's connections. But this is like a time that there was no such thing as female Nepo babies. So just no, sorry, that's not an option. So she actually did her PhD in Frankfurt, Germany, where she was from. And she was working on, she was just doing straight up paleontology for her doctoral research. And she was working on this Mesozoic marine reptile called Nothosaurus. And it had a skull with a natural brain cast in it. And she could see, I think, part of it was partially exposed, which are the most metal looking ones. When you can see them, they're still in the skull, but like only a chunk of the skull is removed and you can just see these brains behind it, which is really exciting. So she got super into this because she was like, oh shit, like I can apply what I know from growing up with a total nerd for a dad and be able to look at the external features of brains in fossil animals and be able to say more about the evolution of brains and be able to have that deep time perspective. Now, unfortunately, her and her family were Jewish and they lived in Germany in the 1930s and 40s.
Not a good time.
Not a great time to be Jewish in Germany. She really didn't want to leave Germany. It was her home. She did lose immediate family members to the Holocaust. And it was actually paleontology that got her out of Germany. She has a quote where she was literally saying, like, one way or another, fossils are going to be how I escape. And it was that Romer, the famous Romer of paleontology, the Romer session, he gave her a unpaid research position at the Harvard Museum of Comparative Anatomy or whatever it's called. And that is how she was able to get a visa to get to the United States in 1940. So she was able to escape. Another interesting fact about Tilly is that she was deaf, not her entire life, but she started to go deaf from this degenerative disease starting in like high school. And so by the time she'd gotten her PhD, she was pretty much fully deaf. And it unfortunately seems like it led to her untimely passing because she was hit by a truck, unfortunately, and did not hear it coming. So there are lots of quotes about how it was, she just had a tough situation. You could be born to a doctor and still have a tough life, y'all. But she was like, okay, so I can see in this marine reptile that it has a natural endocast. I wonder what happens if I fill it with rubber or plaster or later plastic, and then either gently pull it out, and by that we mean break part of the skull, usually, to get whatever your medium is out, and then be able to study those features. So she's looking at things for all of these internal structures, looking at things like, okay, one of the first things that she studied was, again, whales. Sorry, everyone. Whales again. So we know that, parts of your brain have a lot to do with different senses. So, for example, your nose smelling is your olfactory bulbs. So those are all having to do with sense of smell. I think they're generally towards the more anterior portion of the brain. And so she could see that in fossil whales, they got smaller over time, largely because they don't need to smell as much underwater. They might need things that are more of like the hearing and aspects that are being selected for. And so then she really dove into other animals too. She wrote an entire book, I've got it right here, on the evolution of fossil horse brains. She looks at 55 million years of horse brain evolution. And her conclusion was, I want to see if I can read the quote.
They're not as good as artiodactyls?
It made me laugh.
Is that her conclusion?
Yeah, very much so. And that they had weird penises. No, she didn't know that part.
No endocasts of those, fortunately, for all of us.
I don't know why I laughed so hard at this line, but I did. She wrote, while the equidae developed from cat size to horse stature, the brain became progressively smaller part of the body. And I was like, And I was like, I don't know why I'm like talking shit on horses, but I found that really, really amusing. And okay. And before Tilly, before literally trying to interpret fossil brains, scientists were trying to understand like the evolution of brains by just like dissecting modern animals and kind of doing like comparative methods. So it was more of like, oh, I dissected this fish and its brain is like this. And so compared to like a reptile and a mammal, like, which is, informative, but things diverge, things evolve on their own lineages. So it's hard to say the ancestral condition by looking at all modern things. So she was really, really good at being able to figure out the evolution of brains by the skill set of smashing skulls and taking names. It's pretty badass. One of my favorite things I read about and then found copious amounts of evidence for that I was like, I don't know if you were super familiar with her work and I don't know if you were a fan of hers prior to this, but you're going to be.
Okay.
You're going to be. So I was reading this other book I have about Tilly that's mostly in German. Whoops, my bad. There are a few sections that are in English. And this is the quote. To appreciate her kindness to me, one should keep in mind her deep hatred for Marsh.
Yeah, okay.
Which I never fully understood. But in many publications, she took great pains to expose what she considered to be fraudulence of Marsh's science. She was convinced that he invented the images of bird brains from Hesperornis and Ichthyornis that he had published, that she literally, like, he made them up, and that he had never actually prepared the specimens the way she does. And then I guess this guy, so this is Harry Jerrison who wrote this, who said that they were like gossiping like little girls talking mad shit on Marsh. And one of his points is that Coryphodon, which is another Eocene big awkward ungulate thing, a lot of them in Texas as well, that he created like these fantastic pictures of the brain of Coryphodon and the enlarged olfactory bulbs in a Uintathere. Like they're gossiping about how dumb he is because he made a Uintathere brain look like an enlarged rodent brain. Like this was her sassafras.
Such specific gossip.
They point out that you can fuck it up when you're doing these human-made casts, that essentially you might be removing, they say essentially matrix from the cranial cavity, but it's actually bone, and you might not be able to know the difference as you're prepping through it. And so then you can come up with inaccurate relative sizes of the portions of the brain, which is just funny. And so then I was like reading her book, The Evolution of the Horse Brain, and I didn't have to read very far before she just starts talking mad shit on Marsh. And I was totally here for it. And one of her lines, and like this is one of those, I'm going to read it and then explain why I think it's really funny if I can get through it. It's like, because it's academic sass.
Yeah.
I'm just going to say in advance that it is like her being like, fuck you, you're an idiot, but she's doing it academically. So she wrote, one paleoneurological theory of evolution must be briefly discussed. Although the outcome of a typical 19th century ideology, it has found its way into so many kinds of literatures that to test it with the evidence of our study seemed necessary. Essentially being like, this is a ton of bullshit. We all know it's bullshit, but people keep talking about it as if it's legitimate. So here I go again, showing you why this is total horseshit, no pun intended, because it's all about horses. Just like, I love her. And then she like literally spends multiple pages talking about why Marsh was wrong. And the main thing that she criticizes is that Marsh had this theory that as animals evolved, their brains always got bigger, especially in mammals, that the derived mammalians are so superior, which, you know, probably not. Talk to a, crocodile. That, and a lot of her work, as we're talking about with the horses, is that they actually get smaller proportionally to body size. Especially, she writes, once they evolve the muzzle and the Miocene, the brain becomes an even smaller portion of the head, and it has remained that way in the modern day. And so she is just totally reading him for just being overgeneralization and being too focused on function instead of the constraints of ancestry is really her whole point, which is why Stephen Jay Gould loved her like a lot too. So it's just kind of this idea. And I think that goes into what you're going to be telling me about the size of brains and brain regions and why what we think we know might be what we actually don't know. Yes?
Yeah. So there is this concept that is often referred to in the study of endocasts, whether they're sand or otherwise, called the principle of proper mass, which is basically this idea that the size of a region of the brain is proportional to its ability to process information. So that means that like if you have really great vision, you'll probably have a bigger section of your brain that is dedicated to vision. And of course, therefore, that would mean that if you could look at the brain, or at least look at a cast of it, you might be able to determine where basically a animal was investing its brain energy. Is it really big into sight? Is it really big into smell? Is it really big into balance? And as I was reading through these papers, I did notice that Tilly Edinger's concept of, hey, your phylogenetic relationship there is going to really kind of determine a lot of that stuff is absolutely true. When you talk about brains, you really have to keep in mind who they're related to. So, for example, the endocasts of dinosaurs, way different than the endocasts of birds and mammals. So with birds and mammals, our brains fill that space. They push up.
I already love this.
I know. Really, I've been taking, this is week 2 of volunteering to talk about dinosaurs, and it's just week 2 of Megan finds a reason to talk shit about dinosaurs because, so our brains are pretty big and they press up against the confines of our skull. So you can actually do a lot more interpretation of a bird brain or of a mammal brain than you can of a dinosaur brain, because dinosaurs, by and large,
I'd never thought about it like that.
Yeah, so dinosaurs, not all of them, pachycephalosaurs, I imagine just because they don't have a lot of brain space left, they have pretty tightly constrained brains, so you can tell more from their endocasts. I mean, they've dedicated so much of their skull to bone. So like they just don't have a lot of space for that brain. Is my thought.
That's right. They got to get that dome.
So not all animals fill their entire brain case. Coelacanths and basking sharks, less than 1% of their brain space is full of brain. Nobody told me what the rest of it was, by the way. So I've just been envisioning these tiny little brains floating around in fluid. I'm sure that's not really true, but the most of the brain case in a coelacanth or a basking shark isn't brain. It's actually the same with alligators. And I giggled a little bit when you said something about ask a crocodile, because it turns out that with crocodilians, if you want to talk to a big-brained crocodilian, you should talk to babies, because baby crocodilians have a much bigger brain size in comparison to their body than adults do. Because adults might grow their big fat faces, but they don't actually grow their brains as quickly. So baby alligator has about 68% of its brain capacity full of actual brain. So like the actual organ is only like 68% of that space. Whereas adults are like 32%. So a real sharp decline.
What?
Yeah, so that means a lot of things other than just kind of the funny implications of having less brain as you get older. But it also means that because there's not as much brain inside the brain case, it's not pushing up against every single boundary of the skull. So you're not actually getting, like with mammals, you can look and you can see the wrinkles, you can see the different regions of the brain, you can see veins even that are pushing up against the surface. But with alligators, you can see like the different general regions, and in some dinosaurs you can see a little bit more, but there's not nearly as much detail preserved with an endocast because it's a smooth brain as far as the inside of the skull goes, because there's no brain touching it to make brain shape.
there's no mold. There's no wackadoo designs to replicate on the surface of the brains because they're not filling it. And for whatever reason, that hasn't been selected for to decrease that space or use it for something else, right? I mean, like, that's weird, but like, is that just, I guess that works.
I'm sure there's something else in there. This is not probably just an empty space with a brain floating around in it, but I genuinely could not find in the space between this morning when I realized that fact and this afternoon when we were filming this, I couldn't figure out what else was in there. So fill it in with your mental image of whatever else you might imagine is in a dinosaur brain or an alligator brain.
Confetti.
Yeah.
Oh my God. Yeah. Like candy.
Ooh,
candy. Like a piñata.
Yeah. I did read a paper about someone found an isolated hadrosaur endocast with a little bit of skull attached to it. They found it floating in a tide pool. Well, not floating, but rolling around in a tide pool. And when they looked at the actual endocast, it was filled not just with sand, but it was also filled with, it had fossil leaves, fossil wood, and some bone that wasn't its bone. Like some other bone that had gotten shoved into the brain case.
Wow. So, and like that's as complex as that hadrosaur's brain ever got.
Yes. So one fun side effect of all of this is essentially that when you're talking about endocasts, you do have to be aware of like just size alone is not actually going to necessarily correspond to changes in intelligence, but also with certain groups of lineages, you have to take into account the body size and you have to take into account whether it's an adult. And someone used that to talk shit about Nanotyrannus.
Yes.
Yeah.
Oh my God, we're talking about Nanotyrannus on our podcast.
Right? What?
I never thought we would sell out. We are total sluts. Jeez.
So Nanotyrannus, if you're not familiar, is a controversial dinosaur. Some people think it's a juvenile tyrannosaur and not a new species. Other people think it's a new species. I don't care. But what this particular paper said.
Right answer.
They took cast of these different dinosaurs' brains. I think they did CT scanning. So they had to do all of this like complicated stuff because remember, the endocast of a dinosaur is its brain plus whatever mystery goo is outside of that. So they did some weird math where they compared endocasts versus actual brains of alligators, use that mathematical relationship to scale the endocasts of these theropods. And so the big Nanotyrannus diss was that they looked at Nanotyrannus and they found that it had too much brain compared to its body size, which means like alligators, they thought it was a baby.
A juvenile. Mm-hmm. A juvenile. Mm-hmm. Oh, I see. I like that kind of comparison of like it has a larger ratio of brain to body size. Yeah. Okay. Unique. I mean, everyone's digging for every freaking angle they can get with the nano stuff. Right? So here for it. Here for the new perspective.
And one chunk of the brain that seems to pop up a lot and be relatively visible regardless of how little your brain touches your skull is probably one of the stupider words that I had to read. I have a note here that says that this entire paper reads like fucking Dr. Seuss poetry because here are some sentences I highlighted. The protrusion of the flocculus into the fossa. The volume of the nodulus and uvula.
Oh my God.
Yeah. So the flocculus is one part of the brain.
Yeah, tell me about this flocculus.
Yes, the flocculus, which is a word that if I'm not directly staring at it, removes itself from my brain. I don't remember this word. Every time I've scrolled away from this page,
probably
I've
because you don't
it.
have a flocculus.
My flocculus is gone. So flocculus, basically it operates the eyes, neck, and head movements. So you being spatially aware of where your head is and what it's doing. Mm-hmm. Pretty important function, although apparently not in sauropods. So the volume of the flocculus has been analyzed to see if basically how big is your flocculus relates to, how good your eyes, neck, and head movement is. Even though the term flocculus is fucking hilarious to me, I did find it a little confusing while reading today. And so for all of you who study the flocculus, please keep this in mind. There is a difference between the flocculus and the floccular fossa. So the flocculus is the stupid part of the brain that deals with where the fuck your head is. Yeah. And then the floccular fossa is the divot inside of the skull. So the floccular fossa is the only thing you're measuring if you're measuring an endocast. And that is not the full flocculus. So even though there are some papers looking at flocculus size saying like, okay, well, if you have a big one, it probably means you're like a carnivore because you need better understanding of where your head is. Whereas if you're an herbivore, you can just smack your head into leaves, I guess. But the floccular fossa that you're measuring in a dinosaur skull is not the same as the actual flocculus. In particular, we know with birds, at least, birds, their flocculus is actually made up of two different parts, and one part is on the inside of the brain. So like you can't 100% cross-correlate these two things.
Right.
Does that make sense?
Yeah. But I guess you work with what you've got too. You know, it can be hard to clock it when it's like, yeah, no, it's not perfect. And like, you know, you're working with what scant material we have. And then I have to just take it back to what you're talking about. Your like 157 Oriodont brains rolling around all over the place and the individual variation playing enough of a role that it's hard to even make a direct fit. And so then when we're talking about like literally maybe 1 or 2 Nanotyrannus skulls out there and trying to make all these larger, you know, interpretations of it, I just have to like, I feel like that's always my thing with dinosaur people is I'm like, time the fuck out. Your sample size is 1. Like you cannot account for variation in that. Please give me a bigger sample size. And I know that sometimes again, it's not possible. And then maybe just hedge on, let's not create an entire new genus until like we have a little bit more evidence. But you know, woe is me. Don't listen to the idiot mammal paleontologist up in here. So
yeah. So the flocculus is a little bit weird. Apparently also the parts of our brain that control like, I guess our flocculus, that control like our ability to keep smooth pursuit, so tracking a moving object in a field of view. If you get a brain lesion on those parts, your brain can compensate because we have brain plasticity. So even though these regions are like broadly corresponding to these sections, it's not 100% guarantee that the animal hasn't adapted a different kind of method for dealing with that stuff, which is interesting.
Oh, man. Flocculus.
Yeah.
Oh, and I've seen a lot of actual full-blown models of dinosaur endocasts and things like that, which when you look at like a mammalian one, they do look pretty brainy. They look like brains. When you see one of a dinosaur, it just looks like, I don't know, an anthill, like the internal structure of an anthill. I don't know. It's just like, it looks like a weird root system or something, like a carrot gone horribly wrong. I don't know, but they don't look like brains. They just look like essentially cranial nerves that have never actually turned into brain. They're just like blah, nerve brains. I don't know.
Or just like kind of smooth lumps because they're not pushing up against the skull. Like it's,
that's a really good point.
So
that's a really good point.
When we talk about these brain structures can change. One of the, and this is the other stupid word, the Wolst. I even looked it up on YouTube because I was like, how do people pronounce this? YouTube doesn't have a pronunciation option. I've never found a word on YouTube that doesn't have a pronunciation option. But the Wolst is a portion of a bird brain. And it's supposed to maybe like be connected to like your locomotion ability. And so they've studied it in things like penguins, because penguins have really big wolsts. So whatever the wolst is doing for them, it should, in theory, and they've also found that like other aquatic animals often have very big wolsts, but they show up after penguins go into the water. So like very, very ancient penguins don't have wolsts. And it shows up like 25 million years later is when they get a wolst. So like, even though these structures might seem odd in something like a penguin, they often are showing up at different times, and that might be related to brain plasticity.
That they're like making it work. I honestly think it's evolution being like, I know that you're humiliated in your inability to fly, so here's a wolst. Consolation prize. Don't know what it does, but here you go.
Yeah. That's dinosaur brains. Dinosaur brains are smooth-brained. They float around somehow in their skull. Sometimes they bump up against the surface. Sometimes they don't. Babies have bigger brains. Nanotyrannus had a big brain. That's dinosaur brains. What about human brains?
I'll get there. I love this idea that, like, you know, it's like this kind of insult, right? Is to be like, oh, you've got nothing in your noggin. Like, you can hear like a marble rolling around. And to know that now that is like actually supported with concrete evidence about dinosaurs, it just continues to feed my superiority over the most, whatever. I appreciate them, but they're totally overrated. So, ha ha ha, ha 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 ha.
Smooth brain motherfucker.
You know, I was actually thinking a nice end could be, you were just talking about this behavior and understanding like things of just like eyesight, and actually the semicircular canals and cochlear, like the features of the inner ear. I'm going to chat about that for maybe our finale. And so in your inner ear, you've got some funky shit. I know because my son just had his first ear infection. And so we got to look at that poster in the pediatrician's office of the inner ear and what it looks like when it's like pussy and infected, which is what Tracy's ear was looking like. It was literally like oozing out of, it was gross. It was very gross. However, like I've done some CT work at UT Austin. I did a bunch of brain endocasts, but I also did some ears. And you've got these semicircular canals, which are like a series of about like 3 loops that are a big part of how we help with things like balance, and that are literally keeping that sense of balance. So there have been research into especially like mammals and primates, is that there seems to be a selection for having this large, there seems to be quite a bit of variation.
Canals.
Huh?
Yeah. Larger canals, I think. I came across some similar stuff with pterosaurs in particular, is this preponderance towards bigger canals. Were you finding variation was a
that there seems to also be like variation that has to do with literally the curvature of mammalias, and that seems to be that organisms that have large eyes and acute vision have, oh God, is it bigger or smaller? That's what I don't have a link for right here. But essentially, right, being able to interpret an aspect of eye size, which then can also go into like hunting and just overall placement in your ecosystem, can be learned from literally looking at that. And what's also cool is that this paper found that having small semicircular canals tends to be a thing that we find in fossorial mammals and plesiodaphiforms, which are things that burrow. So there seems to be this selection for getting those a little bit smaller for whatever reason. Is it a balance thing? Is it a reliance on other senses and a less reliance on those senses? But we can interpret some aspects of locomotion, senses. Again, these are forms of behavior by looking at the inner ear. And then also the cochlear is the part that looks like a little snail. It's like curvy and windy, and it all has to do a lot with hearing. So again, we can look at the size of that spiral shaped inner ear and get a vibe for, at least, you know, again, this is not one to one, but you are going to have a better idea about that adaptive ability by looking at the size and like how tight the circles of the snail shell is, which you don't actually have a snail shell in your ear, but it looks exactly like that. Okay, yeah. Let me just treat this abstract as the semicircular canals of the inner ear detect head rotations and have to have compensatory movement to stabilize the gaze and help maintain visual fixation. So it's very interesting that eyes are having something to do with your ears, that you would think like, no, those are separate senses, but they can, well, they're all friggin' related. They're all in your own head. So it's just really cool to think that it's not just brains that endocasts can be really useful for. It's also these other hollow places in your body. If it's hollow, we can endocast it. Which is exciting to think about. So yeah, I've had some experience with, all of my experiences have been with the some parts of the skull. So I'd be curious to know about, I don't know if you like, is there soft tissue of like, I was like Googling like intestines, like do we have like endocasts of intestines and things like that? And I'm also realizing that we were just talking to Dr. Ohenia Gold last week, and she works on bird brains. So maybe we'll have to do a bonus thing and chat with her or something like that too, to find out more.
We'll at least have to ask her what the hell is inside of a dinosaur brain if it's not brain.
Yeah,
what is it floating in?
Great question. Thank you for listening. If you liked the podcast, be sure to rate and review us on your listening platform of choice. We really appreciate it.
If you'd like to hear more and support the show, follow us on Patreon for some exclusive bits or on our various social media platforms. You can follow Amy on Instagram at Mary Anning's Revenge.
And Megan on Instagram and TikTok at GeoPedalFabric, or both of us at Weird and Dead on Instagram and TikTok. This podcast is part of the Geology Podcasting Network.
Produced by the traveling geologist, Chris Spencer.
Cover art provided by Chris Spencer and the hosts.
Our theme song is Unlock Me by Praz Canal. Editing services provided by the amazing Katie Bradley.
Hosted by and researched by us, Amy Atwater and Megan Weatherall. Thanks for listening. We'll tell you all about an insane brain bonanza in West Texas and stumble through medical terms for tissues that don't usually flossilize. God damn it. All right, we'll try that. That was perfect.